Hello, my name is Dean Chalmers. I'm the Astronomy Technology Manager at the National Research Council of Canada's Hertzberg Astronomy and Astrophysics Dominion Radio Astrophysical Observatory. I'm also the NRC NGVLA Antenna Design Project Manager. And I'm going to present to you the NRC NGVLA 18-meter antenna design concept. The contents of this talk will be, we'll talk a bit about the design study and give you some context, talk a bit about the composite reflector technology developed at NRC, and then have a look at the NGVL 18-meter requirements and go through the NRC design concept and a little bit about the performance analysis conducted so far. The design study was kicked off in January of 2018, and our NRAO requested NRC to produce a design concept for the 18-meter NGVL antennas based on our composite reflector technology. NRAO did not expect the requirements for the NGVLA to push technical boundaries, but was looking for an innovative design that would meet the performance requirements and be suitable for volume manufacture. The intent of this design study was to provide an alternative novel design to complement a more conventional design envisioned to be the reference design. In the end, the design presented here was selected to be the reference design for the NGVLA. A little bit about our composite reflector technology before I get into the design. The reflector technology is based on the vacuum infusion process. This is a technology that is commonly used in marine, civil works industries and is increasingly being used in the aircraft industry, as it allows you to make large, high-quality parts without needing expensive infrastructure such as an autoclave. There's also a much cleaner and more worker-friendly process. The fiber materials are laid on the mold dry and covered with a sealed bag and are drawn down with a vacuum. The vacuum is then used to draw the resin into the activated resin into the part. The image shown here, you can see the white parts are where the resin is the dry fabric, and the black parts are where the resin is flowing in from a manifold system on the part. The key to the success of this project with really large parts is the modeling of the infusion process to ensure complete resin infusion. And one of the keys to NRC's technology is our ability to include a radio-reflective layer in the layup of the part. So there's no need for post-coating or adding surface on. This development started in 2006 as a technology development for the SKA. The first two reflectors, Mark I and Mark II, were 10-meter symmetric reflectors. The Mark I was infused with structural beams on the back, included on the backside, and this resulted in a surface figure of about 1.2 millimeters RMS. Much of the surface distortion came from the backside beam structure printing through onto the surface. For the Mark II, the design was changed to a central hub with radial beam structure, and the beams and the hub were made as separate parts. So the infusion just included the surface and the rim, and the hub and beams were bonded on afterwards. This resulted in a much better surface accuracy of 0.5 millimeters RMS. The next step in the development was driven by SKA's choice of a 15-meter diameter offset Gregorian antenna as their reference design. Working with the US SKA TDP program, the rim-supported concept from the Minex ATA antenna design was adopted, and the single-piece rim-supported composite, or SRC, reflector composite concept was born. In 2014, the DVA-1 antenna was completed, and despite having had surface turned inside out in transport and repaired, it achieved a surface accuracy of 0.8 millimeters RMS, meeting the original SKA requirements for 10 gigahertz maximum operating frequency. Recognizing the need to reach higher operating frequencies for the NGVLA, the original DVA-1 mold was reworked to target operation up to 50 gigahertz. The backup structure was also redesigned to provide greater stiffness. Limitations in the design and materials of the mold and the DVA-1 mount precluded trying to reach higher frequencies, but pushing to 50 gigahertz was seen as a good step using what we had to work with. The DVA-2 reflector was produced in 2017 and achieved 300 micron surface accuracy. Key requirements for the NGVL 18-meter antenna are shown here, and the ones that are driving the design are shown in the red text. I guess I should have actually had the 18-meter diameter in red, because that is certainly driving it. The 244 quantity is driving design for manufacturability. The offset Gregorian with the feed lower focus point on the bottom, as described here, significantly impacts the mount geometry. Surface accuracy requirements are pretty stringent, not ALMA level, but for an antenna of this size and with a single piece composite surface are a challenge, and the pointing will be a challenge for an antenna of this size. So this is the NRC NGVL 18 meter offset Gregorian shaped optic single piece rim supported composite reflector with an alt-az pedestal mount. It has features include single piece composite primary surface, of course, a composite outer backup structure, a steel inner backup structure, a composite feed secondary support structure, single piece composite secondary reflector, and a relatively conventional steel yoke and pedestal structures, although the yoke is somewhat novel configuration to accommodate the offset feed low reflector. The design is adaptable to either a direct drive or conventional geared drives on both elevation and azimuth axes. The primary surface is a carbon uniform thickness carbon fiber. There's no rims or other features, beams or other features on the back of it. An INVAR mold will be used, and we've just recently discovered that INVAR molds are actually affordable for an application such as this and provide an incredibly stable, accurate mold can be achieved. The uniform thickness of the surface and low shrink epoxy resin combined with the quasi-isotropic fabric layup all are important in achieving the high surface accuracy. This is a picture of the surface and the mold, which will be shipped in pieces and assembled on an isothermal base. Composite outer backup structure is assembled from 10 panels in a conical structure, and then the primary surface is supported by approximately 200 adjusters, providing near continuous support around the edge of the surface and providing the ability to fine-tune the surface shape after assembly. The conical butt structure is made up of 10 chord composite panels, and the bus would be pre-assembled and attached to the primary surface while the surface is still on the mold to capture the mold surface shape. Tailoring of the materials used in the outer bus can provide a transition between the very low CTE carbon surface and the much higher CTE steel inner backup structure. And this is the steel inner backup structure. It's a weldment from structural steel sections, makes a transition from the composite outer backup structure to the elevation axis and drive arc. We've used topology optimization software to come up with a design for this, and you can see the optimized structure on the left. It's a very organic looking structure and a thing of beauty, but very difficult to manufacture. So a rationalization is required and comes up with the structure shown on the right. The drive arc is made massive to enable it to be a counterbalance and is adaptable to either a conventional sector gear or to magnets for a drive similar to the AEM ALMA antennas. Secondary feed support structure is also a carbon fiber structure, carbon fiber tubing to make it stiff, light, and thermally stable. The attachment points to the primary reflector are carefully designed as to minimize the loading of the primary surface. Less detailed design work has been done on this structure at this point than some of the others shown here. The mount design. The design goals of the mount were to design it with steel plate materials used efficiently, all components to be transportable, easily assembled, so probably machine surfaces in the factories. Yoke, as bearing and support section assembled indoors at the factory, and then minimum yoke arm length to reduce deflection, and a minimum offset between the L and as axis. And the big challenge here is to accommodate the low elevation angles with the feed low offset reflector. And this is you can see here what has been done is we allowed the arc of the drive arc to pass through an opening in the yoke therefore allowing much stiffer structure across the yoke arms and effectively shorter yoke arms. See a cross section here where that pierces down, and here's what it looks like when it's in this position. Drive design. The elevation drive shown here is a direct drive system with the motor segments in this structure that comes off the yoke and magnets on the drive arc. The system also could easily be adapted to a conventional geared sector gear drive, pinion drive. The azimuth drive is also amenable either to direct drive or conventional motor gear drive. Shown here are two versions of direct drive with either internal or external motors, and shown here is a cutaway of the yoke with conventional drive motors and would be a ring gear on the azimuth. Further study is necessary to find the optimal performance, cost, and maintenance solution. Few analysis results. This is surface accuracy under gravity load at 15, 60, and 90 degrees. Worst case is 66 microns at 15 degrees. And you can see the effects of the attachment points of the secondary support on the left side of those images and top and bottom. Wind loading is a typical wind loading plot under normal conditions with 90 degree wind, 90 degree azimuth, so coming from the side of the reflector and with the reflector at elevation angle at 66 degrees. You can see in wind loading, it's very stiff, only at 21 microns. And some thermal analysis. Under thermal loading, the thermal gradient along the long axis, we saw no gain loss. When doing the thermal loading, we realized we couldn't use a conventional best fit parabola and Roos equation type analysis because it's shaped optics. And so to determine losses, we took the FEA results into GRASP, did GRASP simulations, and then we could back out an equivalent RMS based on the gain loss. And so you can see on a 20 degree thermal, there's about 138 microns of surface accuracy based on a 0.13 dBi loss. Putting those all into the surface accuracy budgets, you can see at this point we're a little over the requirement on the precision operation, but under the requirement on normal. And there's a significant contributor is the 86 microns in the process induced distortion. This is being studied at the moment, involves studying the process, the mold, simulating the mold in the process, and then determining the process induced distortions. So that's the difference between the part and the mold shape, essentially. And finally, the pointing, depending on using assumptions based on ALMA experience and other telescopes with corrections from pointing model and tilt meters, we come up with numbers that meet the spec. But again, more work is required here, and further down the road, we'll refine this. And that's the end of my talk. I'd like to thank all our contributors and also thank you for watching, and you have a good day.